Greetings, aspiring scientists. Welcome to my lecture today on alloys and polymers for the IB Chemistry SL curriculum. So let's get started and go to my slides here. We'll start with 2.4.3. This is alloys. So this is really building on both metallic bonding and sort of mixtures, homogeneous and heterogeneous mixtures that we studied in almost the very first lessons. But it does belong to these material properties units in the IB curriculum. So alloys, let's try to define them. They are homogeneous mixtures of a pure metal, main thing, with some other elements. Could be metals or non-metals or whatever. The other elements can be basically anything. If they exist and create a homogeneous mixture, we call it an alloy. So the percentages of the solute contained in the alloy are lower than 50% and sometimes less than a few percent, but usually they're going to be much less than 50%. They're going to be small amounts. But even small amounts can have big effects on strength, conductivity, corrosion resistance, and many other properties. So we'll consider that today with a few examples. So an alloy is a major metal, the main thing, providing the kind of solvent. You can kind of think of alloys as a solution of two metals. So the solvent with a homogeneous mixture and alloying elements as the kind of solutes. So some examples here: brass. Main thing is copper. Added to it will be zinc. You can find this in some door handles, window fittings, screws, musical instruments, quite a few different things. Steel, then, I'm sure you know, very important. So it's composed mainly of iron with some carbon and some other elements depending on what kind of steel you want to make. So infrastructure like bridges, buildings, also a lot of tools like cooking things, construction things, whatever you can think of. A lot of them use steel. And then dental amalgam. I don't think we use that much anymore, but it used to be made of mainly mercury mixed with silver and tin. You probably have heard that mercury is toxic, but it's really only organomercury, or mercury that can enter your bloodstream and cross the blood-brain barrier, those kind of things. Mercury alloy like this, I guess, was quite safe and stable and just replaces or fixes teeth. So used by dentists for teeth fillings. So some alloy properties. Alloys can and often do have a number of more desirable properties than the base elements. They have potentially greater strength in terms of, forces being applied. Can it resist those forces? Greater resistance to corrosion. Sorry, let me fix that. So they may not oxidize or corrode as much or as quickly. Enhanced magnetic properties, greater ductility, so might be able to be reshaped or pulled into wire shapes more easily. So these are possibilities and often the case. So why would having an alloy, having some impurities or some solute particles in the metal, increase its strength? We could think about this. I showed you a little animation in my previous metallic bonding video, how the layers of metal in a very organized crystal structure, the cations can slide past each other, and that leads to deformations and plasticity and malleability rather than cracking and breaking. With a strengthened alloy, though, it's going to be difficult to get it to do either of those things, to change its shape or to crack. It's sort of resistant to those things. So you can kind of see, if we apply a force, the impurities create irregularities or abnormalities in the crystal structure, and you'll kind of have these big particles electrostatically and just spatially resist any movement of things around them due to their position. It's harder to push through that. And even the smaller ones here, it might look like there's extra space here. I just couldn't really show it, but probably these particles around it will be able to get closer and therefore also block movement of these layers, block slippage that way. This is an oversimplification, I'm sure. If you go watch like Veritasium YouTube's channel videos on, I don't know, airplane engines or other types of metallic things like the forging of swords, you can see it really comes down to metallic crystal structures and grains and sort of levels that we're not really looking at in IB. But this is a simplification that I think can get the point across, that these layers will not slip as easily. So after the force is applied, there's not much change in the strengthened alloy, but in the pure metal, layers can slip and we get deformations. Okay, other examples. We can have some alkali metal alloys, Na with K. I think it's just called NaK sometimes, NaK. Liquid at room temperature, used for nuclear reactor cooling. I guess it has some very good thermal properties, thermal conductivity, and perhaps capacity, I'm not sure. But as a liquid, flowing easily, can transfer heat very well, I think. Nickel with titanium, also known as nitinol. You should definitely go watch some videos of this if you have time. It's a very strange and unique alloy that can deform for long periods of time. But if you change the temperature, it can retain and remember what its original forged shape was, which is really cool. Fe with C, iron with carbon, generally what we call steel. So iron is common, but not particularly a strong pure metal. It's quite malleable and weak, I think. But adding just a little carbon makes it very durable and able to resist forces. So iron with carbon and chromium is not just steel, but it's stainless steel, a special kind. So adding 11% or more chromium causes a protective layer of chromium oxide to protect against oxidation and corrosion. You can also dip steel in molten zinc for a similar effect. You can get, I think, zinc oxide coating on the outside, which blocks further corrosion. That's galvanizing. What else? Copper with tin. Sn is tin. That's bronze, one of the first alloys created by humans. Bronze is harder than pure copper and pure iron and more resistant to corrosion than either. So this was used in the Bronze Age in history for weapons, tools, buildings, one of the first sort of ages of metal that we had, I think. Then copper with zinc, brass. So I think we talked about brass in my previous video with the bonding triangle, how it was like metallic bonding, but more towards the covalent side, and we predicted that it might be brittle. But here's a case where that prediction doesn't really follow through. Those are just guesses and guidelines, but in this case, brass is highly malleable. It's antimicrobial, clear acoustic properties. It's good for door handles, railings, musical instruments, and so on. So even though it has covalent character, when it comes down to the actual metallic crystal structure and the way the grains and things are organized, it ends up being able to slide layers past each other very well. So here's sort of an exception to what you would predict on the bonding triangle, I think. And then here's a Google Gemini generated image, but it shows that there are slight differences in color and sheen and the way that these metals exist. So let's talk about rust. Why is rusting so bad and what is it? So rusting of steel or iron oxidizes it. It will produce iron 3 oxide, Fe2O3, which often contains, I think, water in its crystal structure as a kind of hydrate So Fe2O3 is much more of an ionic compound, big electronegativity difference between iron and oxygen. We'll have iron 3+ and oxygen 2- in this ionic structure. So that has very different properties to iron. It's more ionic bonding. So it's relatively weak, brittle, bad conductor, and unappealing color, this kind of dirty, dark orange brown color. And furthermore, because of this weakness and brittleness, it will easily flake off, chip off, and reveal the next layer of fresh, vulnerable metal underneath. So you often hear one of the worst things you can do to a rusted thing is to chip off the rust, because it will just allow the next layer to quickly rust again, and you'll lose more of the fundamental structure or body of whatever you're dealing with. So we'd like to prevent rusting and corrosion as much as possible for the things that we design and build. And then this is just something I kind of like to show my students, the life cycle of potential metal that we mine. Metals are quite valuable, so we'd like to try to refine them, purify them, and recycle them. So we can mine the ore, but it is often in the form of an oxidized oxide, iron oxide, copper oxide, whatever. So we'll crush the ore, purify the metal, often might involve chemistry or smelting or different things. So we'll get the mineral first, extract the metal through smelting, get metal ingots, shape it through applying forces and presses and things like that. We'll form our products, maybe like aluminum can in this case. We'll use it, we'll have it the end of its useful lifetime after it's been sold and somebody drank it, crushed it up. We hope we could recycle that waste metal and use it again, but it's possible that it might be thrown out into waste as well. But we'd like to keep that cycle of recycling metals and making new products as much as possible, because mining and processing it is fairly difficult. Some practice explain why alloys tend to have more resistance to deformation by external forces than pure metals. So I'm pretty bad at drawing this, but you could just go back to my previous slide that shows this. Instead of a regular crystal structure, we might have a much more irregular sort of system here with cations of various shapes. So this whole thing is not going to slide as easily when force is applied. Layers do not slide as easily. Okay, I think that's the main reason. Then number 2 suggests why the electrical conductivity of an alloy is often lower than that of a pure metal. Okay, so this one you might have to think about. I do have an animation to show this, but think about it first. Think about my animation that showed why pure metals are great conductors. They have a highly organized crystal lattice of cations, and especially when it's cold and they're not vibrating very much, the electrons have a clear, straight path through long distances. And when electric field is applied, they can travel unhindered or unblocked through that pure metal. What about the alloy that I just drew over here on the top right? Does that have clear straight lines through the metal? Not really, right? Especially where there's those big cations. It's blocking several pathways. Electrons couldn't easily travel in a straight line through that. So maybe I can show that on the following slide. Okay, and I think this is what you should try to draw if you're asked why alloys might have lower conductivity. So we can see there's kind of this lattice here. It has the base metal, the kind of gray ones, larger impurities, purple, and smaller ones, the orange or yellow. And the structure would be even more disorganized than what I've shown here with these nice columns and rows. Like the big things would push things away from it, and the smaller ones could potentially have more atoms come closer. So these rows and columns, I think, wouldn't even exist nearly this nicely. But even this size, I'll show, has quite increased chance of collisions. So this is impurity content, 30%. But look at these electrons having, pretty high chance to collide with these big fat impurities. It reduces their straight line path and will have collisions that lead to electrical resistance. Okay, so hopefully you see what I mean by this. I think the real effects are even more the case, more obvious in real alloys. This is just a little simulation. Okay. So I think that brings us to the end of alloys. There's not really much, just review the key points that I discussed. Why they are stronger, why there's differences in conductivity. So then we get to 2.4.4. We'll also talk about polymers today. We have some more time, so let's get into this. You've probably heard this word, but might not know exactly what polymers are. I think we can describe them as sort of in between covalent networks and covalent molecules. Covalent networks are like trillions and trillions and trillions of atoms all covalently bonded together in one continuous kind of bonding structure. Molecules often have maybe 2 or 3 or 4 or 5 atoms stuck together in a molecule. Those molecules are then held together by intermolecular forces. Polymers are kind of in the middle of that. So, polymer introduction. Polymer, what is it? It's a very long covalent chain. It's almost a network, kind of. We're talking about hundreds of thousands of usually carbons linked in chains. So compare that to trillions, trillions, trillions. It's actually quite a lot less, much, much less than a full network, but it's much more than the 2 or 3 or 4 or 5 atoms we might have bonded together in a molecule. But you still could think of these as molecules, but they're often referred to as, polymer chains. So what's a monomer then? So all polymers are sort of repeating units of something that was used to build them. So the single unit that was used to make them is called the monomer. So in Latin, poly means many, mono means one. So if you can remember those little prefixes, it will help you name these. So what is addition polymerization then? This is the process of turning many monomers into a polymer through addition reactions, where things are just added together. So we also have special polymer notation. We can have the monomer, we have N monomers coming together to make a chain that is N units long, which contains the repeating units of polymer. So in this case, we have a CC double bond and then different groups A, B, C, D on it. But that double bond, the second part of that bond, will open up and attach to other nearby monomers. And sort of this chain reaction happens, I think. We get the hundreds of thousands units long polymer then. But the A, B, C, D are essentially in the same spot as where they were on the monomer. They'll just repeat over and over on the long chain. More vocabulary. Macromolecule. So a very high molecular weight molecule, often produced by some kind of polymerization. And I think this vocabulary is often used in biochemistry and biology. So macromolecules include things like carbohydrates, proteins, lipids. What else? Synthetic polymers. So polymers made by humans, not found in nature. We can have things like Kevlar, like body armor, nylon for clothes, polyethene for plastic stuff. We can also have natural polymers. These polymers are found in nature. Things like silk made by silkworms or spiders, DNA, you might not realize it, but it's a very long chain that contains carbon, oxygen, phosphorus, nitrogen, many different things, but it's a natural polymer. Starch mainly contains sugars, cellulose as well. Then condensation polymerization. This is an HL topic, but I think I should introduce that it exists here in SL. So it's a method of polymer production similar to addition, but instead of just addition, we link the monomers together by elimination reactions. We're going to eliminate some small molecules. Oftentimes it's water or HCl possibly. Instead of opening double or triple bonds, we'll eliminate small molecules. So you might not be able to quite picture this or imagine this yet, but hopefully this animation will help. Imagine we have a lot of ethene molecules, these carbon-carbon double bonds with hydrogens then. Sorry, my H labels are a little off, but those little white balls are hydrogens we can consider, so each carbon has 4 bonds. So we have a bunch of ethenes hanging around, but they will start to potentially polymerize through addition by opening up the double bonds and create long carbon chains like this. One more time. So this kind of chain reaction happens, the double bonds start to open, and we get one long chain. So this can go on hundreds of thousands of times and produce our long chain polymers, polyethene. So, polymer properties and why might they have them? So most polymers can be made to be elastic or brittle. We can kind of modify their malleability and elasticity and brittleness depending on cross-linking between chains. So cross-linking you can think of as having 2 long chains. Sometimes there's another chain of carbons in between them that will link them together. Sort of shorter chains, but links very long chains together. So most polymers melt at moderately high temperatures and are bad conductors. Okay, there's not mobile charge carriers in, for example, polyethene that I just showed on the previous slide. It's just carbon single bonds, carbon hydrogen single bonds. But some of them could be made to have conjugation and delocalized electrons similar to graphite, I think. Why would they melt at moderately high temperatures? Well, they don't really have the same kind of interconnectedness as covalent networks or ionic salts, but they do have very strong intermolecular forces, right? If they are hundreds of thousands of long molecules, essentially, then they're held together by London dipole-dipole and hydrogen bonding. So the bigger they get, the more electrons they get in their chain. The longer they get, the more surface area they get, the stronger the intermolecular forces will be. So they can get very, very strong indeed. Most polymers are strong physically for the same reasons, very strong, things like London forces, and a lot of stacking going on between these long chains. So most polymers are not chemically reactive and do not decompose when thrown away. You can think of the plastic things that you know, plastic bags or bottles. They would take a long time to decompose naturally. And that's just because they don't react with oxygen or water or any of the things that might normally break down things in the environment. Even acids or bases, usually they're quite resistant. Just the carbon and carbon hydrogen bonding is strong and stable. So for naming, most polymers are officially named poly and then the monomer. Okay, polymonomer is not a real name, but just if the monomer was ethene, like on my previous slide, we'd have polyethene. If the monomer is styrene, polystyrene. If the monomer is vinyl chloride, the polymer is polyvinyl chloride. So just take the monomer name and put poly in front. That's the polymer name. So some practice here. Draw the repeating unit of each of the polymer sections below. Let's try that. So we've got this polymer, we can assume is extending in the left and right directions, but the repeating unit, we've got all H's on the top, then HC2H5, HCH3, HC2H5, HCH3. So if we wanted to remake this polymer, what do we need to copy and paste? It is this section here to this section here. You can see that's a direct copy of the unit to the right of it. So the repeating unit has carbon-hydrogen bond, carbon-hydrogen bond, carbon-hydrogen bond on top, then C2H5, this kind of ethane chain, ethyl chain, as it's called. Then carbon-hydrogen, carbon-hydrogen, and then carbon-hydrogen, CH3. It's a methyl group. So we use these square brackets through a bond that's sort of exiting the structure to show that it continues on, but we have n units of this in the polymer for however long that polymer is. So that's the repeating unit of this example. What about on the right here? Much more complicated thing. This looks like a biopolymer with glucose. So you kind of have to think about this. It looks like it might be 2 of these units that we can cut and paste and create the polymer again. But one thing you probably need to think about is what bonds can rotate. So for example, this carbon-oxygen bond is just a single bond. In theory, it can rotate around clockwise or counterclockwise. And if that whole structure flips through that rotating bond, and also this one can rotate, I think you will essentially get the exact same structure as what is to the left of it. And that means you can actually cut and paste just one of these little hexagon units over and over and over to recreate this polymer. So I think it's fairly difficult to draw. But maybe we can say this here. Only include one of these oxygens on the left because we don't want to double up on these. One of them linking the repeating units is enough. So it's hard to draw, but hexagon, OHH, HOH, H, then extending bond. This one here is not a carbon, actually, it's an oxygen. H, CH2, OH, H, oxygen, extending bond. So in theory, this repeated should cover this whole polymer through rotations. So we'll use the square brackets to show extending bonds going through it. N of this can create this polymer again. Now, I was actually doing some research on this and cellulose, and there's kind of some debate, I think, about how much this can actually rotate. So obviously, if it's blocked by, physical things around it, or possible electron donation or slight pi bonding around that oxygen, it won't rotate it. It will not rotate as much, and therefore the repeating unit might be considered 2 of these instead. I think there's some arguments for that. But if we just assume those single bonds can rotate, we'll say that one of these is the repeating unit. And I think that is the answer that most textbooks would give. Then last here, draw 3 repeating units of the polymer with the structure underneath here. N number of CH with a hexagon with a circle in it. That's a benzene ring or phenyl group. And then CH2. So this is kind of as easy as it sounds, I think. We'll just draw this 3 times. Oops, not CH2, but CH. phenyl group, CH2, CH phenyl group, CH2, CH phenyl group. Should be a six-sided thing, and then CH2. And then that will extend to show that it continues, square brackets. So that's 3 repeating units of this polymer. So you should be able to do both, identify the repeating unit in a section of a polymer, and then extend one repeating unit or even a monomer into some section of a polymer. Okay, some other examples. Cis-1,4 polyisoprene repeating unit is like this. This is the skeletal structure. So just a reminder, any of those little corners or vertexes is a carbon, and anywhere where carbon does not have 4 bonds is hydrogen. So we have a double bond in there and a methyl group in there, an extra carbon pointing to the bottom left. Then all that connects and will repeat throughout the polymer. So this is used for elastic bands, clothes, tires, machinery, belts, and gaskets. So this is actually natural rubber. If you've ever considered where rubber comes from, the natural rubber type is this, cis-1,4 polyisoprene. So it is actually natural. It's one of the only, I think, really long carbon-hydrogen chains in nature that we've really found. And it is made through addition polymerization. Polyethene, so this is just carbon and hydrogen, carbon with 2 hydrogens attached and then connected to other carbons on the sides. Very common, simple plastic for packaging, shopping bags, toys. This is synthetic though. This doesn't really exist in nature. It was made by humans, and it is also addition polymerization. We can then have cellulose. The repeating unit is the sugar glucose here, I think. So this is mainly used for cell walls, paper, cotton balls. So this is a natural polymer made through condensation, not addition. So this will be made by eliminating water molecules on the edges of these sugar. Then Kevlar, kind of a strange structure here, nitrogen, oxygen, and benzene rings. So for sports equipment, body armor, it's quite a strong structure, I think, but it is synthetic, not found in nature, was made by humans, and it is also made through condensation, polymerization, I think through amide bonds, this sort of N-C double bond O linking. Okay, so just some examples of natural and synthetic versus addition and condensation. So what will change polymer properties? This is where things get even more confusing. My students often have a difficult time with this, but length of chains, I think, is a big thing. The longer the chains get, there's more chances for intermolecular forces, more stacking, more London forces, and also for entanglement. This is kind of, you can just imagine some like, I don't know, wires or charging cables or headphones or what else? Just ropes, like any sort of long chain thing. When you mix it up with neighbors, oftentimes you get knots and entanglement, it's called, right? This kind of increases the strength and the stability in some sense. It's difficult to pull those chains then apart if they're sort of knotted up and entangled with each other. So that will happen more as they get longer. Functional groups then, is there going to be strong dipole-dipole, or especially hydrogen bonding? Is hydrogen bonding possible, or is there only London? If there's hydrogen bonding possible, it could increase the strength and stability. Branching of chains. So this is different than length or cross-linking, but branching is sort of chains on chains, right? So instead of just one long carbon chain like this that extends off, You can have chains on the chain of varying lengths. But generally, this will mean less ordered crystal structures. There's sort of randomness in this, and many more chain endings. Chain endings are kind of a weakness of the polymer, where you might have more reactivity or more ability to be digested by biological organisms. So overall, extra branching generally leads to weaker physical properties. But sometimes we want that as a more desirable property. So a very good example to consider is different polysaccharides. These are, if a saccharide is like a sugar molecule or unit, polysaccharides are sugar things like glucose put together into a polymer. So we could have starch, I think like it's called amylopectin is one of the most general cases of this. So this has long sugar chains that is moderately branched. Every once in a while on the chain we'll have little carbon or little sugar chains branching off of this. I think they're generally the same, like repeating unit. It's just they connect onto the main chain and form some branches. So this is a way for organisms to store sugar molecules, energy molecules, for long-term storage. So things like potato and rice and whatever else, wheat. We can have starch, polymer molecules, macromolecules. Then glycogen. This is highly branched, so highly disorganized, less stable crystal structure. We have branches on branches maybe, and very often. So this is a way I think that especially animals will store sugars and energy very quickly, but also have it in a form that it can be digested and removed from storage very quickly. So the instability or the many endings on the chains of glycogen make it easy for your body to redigest it and sort of place those energy molecules back into the system instead of storing them. Cellulose then is kind of the opposite of that. It has basically no branching, and so it will have a very organized and stable crystal structure. So I think this is the reason why we don't digest a lot of plant materials very well. They end up as undigestible fiber if you try to eat like grass or a lot of leaves that has a lot of cellulose and can't be digested. So much more stable, used for things like cell walls. Some practice discuss whether or not you expect an average polymer to have a high melting point or electrical conductivity. So I've discussed that a little bit, but I think we can say medium melting point compared to other things. So it's higher than covalent molecules normally are by quite a lot, but it's not really as high as strong metals or alloys or salts. So lower than crystal networks. But higher than covalent molecules. Okay. Conductivity, very low conductivity. Unless there is somehow conjugated delocalized electrons in the structure. And I'm sure there are labs out there that have designed conductive polymers. but they've got to have some way to move charge through them, delocalized electrons. Okay, so move on. There can be acid and base, or pH, effects on polymers as well. We haven't really studied acids and bases, what they are, in my videos yet, but generally acidic conditions cause H+ to attach to several areas of many polymers. And basic conditions will remove H+ from several areas of many polymers. This can change the electrostatic interactions and the forces between certain areas. So if we have this thing called a hydrogel here, this can expand or contract given different pHs or different acidity or basicity. So in acidic conditions, we have hydrogens attached everywhere in this structure, this sort of carbon double bond OH groups. And they can hydrogen bond with each other, form this kind of dimer structure. So this will contract the hydrogel. But if we go to basic conditions and start removing H+ from this structure, we're going to have a lot of negative charge be left behind on the oxygens. No longer will there be hydrogen bonding. In fact, there'll be strong electrostatic repelling from the O- and the lone pairs. So this will cause the structure to sort of repel and open up and expand. I don't really know the practical uses for this. I think this is similar to what might happen in things like contact lenses. They might be made of hydrogel sometimes, but things like that can depend on pH very much. So this is not only pH, but similar things can happen with temperature, even magnetism, even salinity. The salt content of the solvent of whatever this is in can also affect polymers and proteins, which are a type of polymer, in this way. Pretty important for biology. So let's discuss plastics a little bit. Plastics are synthetic polymers, usually made from crude oil monomers, things like polyethene, polystyrene. So polystyrene is styrofoam. It's a very widely used polymer because it has moderate strength, but it can hold air pockets. It ends up sort of foaming up and having all this air in the structure. That makes it a great insulator because air does not conduct heat well at all. So the more air you have in a structure, the longer it will take, heat to transfer through or out of a system. It can also be melted and reshaped fairly easily to make all of our food containers and cups and things. Then PET, polyethylene terephthalate. I say that 10 times fast. That's a durable plastic used for many food containers and household materials, plastic bottles. And I think it's one of the polymers that can be recycled somewhat. So these plastics are being produced on a large scale, but they do not decompose or biodegrade easily. Biodegrade is sort of the biological way of decomposing where plants, animals, bacteria, fungi, whatever, would break down these large molecules into smaller fundamental pieces. So these polystyrene, polyethylene terephthalate synthetic polymers made from crude oils do not biodegrade easily. They've become a huge waste problem. So long carbon chains are strong, they often cross-link, they have few access points where bacteria or whatever could digest it. So let's look at the structure of these. Polystyrene comes from the styrene monomer that has benzene rings and then some hydrogen bonds, carbon hydrogen bonds. So you can just observe that structure for a minute here. This again would extend hundreds of thousands of times left and right, but this is the basic structure. And that's like our coffee cups, the white styrofoam structures. Then polyethylene terephthalate, PET bottles, is a more complicated structure. It's going to have some carbon-oxygen double bonds, some carbon-oxygen single bonds. I think this is kind of like an ester linkage, it's called. And also some benzene rings in there, the hexagons. These make the plastic bottles that we often see polluting streets or beaches. We would hope to reduce that for sure, but these are not broken down easily, so they'll exist for probably hundreds of years in the environment. So a big area of study is how do we make plastics more biodegradable? The goal is to make plastics that maintain their properties of strength and flexibility for a long enough time period, but then can be broken down by natural processes in the long term, or in the short term. Oftentimes we would want them to not take hundreds of years, right? You know, under 1 year would probably be better. So this can be done in several ways. Shorten chain length, eliminate cross links and entanglements. This will, you know, lower the stability of that structure. Increase available surface area and chain endings, so we can have reactivity and things like bacteria and enzymes break them down. Addition of functional groups that microorganisms can latch onto. So microorganisms are often evolved or designed to attach to things like carbon-oxygen bonds, carbon-nitrogen bonds. We break down proteins and carbohydrates that have those. So just straight carbon-hydrogen chains are much more difficult for organisms to break down. Let's have some different functional groups like oxygen in there. And then addition of light-sensitive or weak bonds where we could maybe control when we want to break them down by shining some light of particular wavelength perhaps, or energy on them. But we have to balance this with the fact that all of these will weaken the polymer, right? So if we need strong things, this will make them weaker. We need to kind of balance or trade off. So great care must also be taken about the way that plastics degrade so that toxic chlorinated compounds or greenhouse gases such as methane are not released. You can imagine if some of these polymers break down, we're going to release chlorinated organics, which are very toxic and bad usually. We're going to release possibly methane and CO2. That's going to contribute to greenhouse gases. So ideally, we'd like to break them down into like food, like not macromolecules, but smaller sort of molecules that can be used as fuel or fertilizer for like trees and plants and animals that can support our environment. But that's quite a challenge, quite a tough thing to design. But I think that's the goal in the end. Microplastics then. Plastics can physically break down easily through repeated trauma or rubbing, like friction. This does not significantly change the chemical structure of a polymer, but it just breaks it into smaller pieces. So instead of 100,000, you'll break it into 50,000 and 20,000 smaller pieces. Any pieces smaller than 5 millimeters are called microplastics and can enter the bodies of multicellular organisms when we consume them. The health effects of this are really not known yet. You can do some research yourself, but it seems like the effects are not immediately obvious, and we don't have many long-term studies to show what the effects of having these little plastic pieces in our bodies or in the environment really is. But obviously they weren't there before, so it would have been better to not have them, most likely. Practice then outline the challenges of recycling plastic waste and suggest structural features at the level of bonding that can lead to higher biodegradability. So challenges are long chains are often stable. Often stable. They could degrade into toxic products, or at least undesirable products, greenhouse gases. Those are some challenges. Then some structural features that could lead to biodegradability. We could say shorter chains to make it simple, and then functional groups with like oxygen or nitrogen that can be biodegraded by organisms. ON, maybe phosphorus, phosphate, for example. All right. Some ideas. So then 2.4.5, this video is almost an hour long, so I want to just go through this quickly. Basically, I've already covered everything that's in 2.4.5. I'll just go through it for the sake of completion. So this is just really focused on addition polymers. The exact same slide, you can review this. Polymer chains, monomers, addition polymerization. This is the notation for writing them. Same vocabulary, macromolecule, synthetic polymers, natural polymers, condensation polymerization. Same animation. Quickly, we show again. Addition polymers specifically are made by these double or triple bonds opening up to link with nearby neighbors and create one long chain. So here are some examples. If we have a chlorine in the top right, when this polymerizes, it's also going to have a chlorine in the top right of the repeating unit. But again, consider that single bonds can then rotate. So this can really rotate to be top or bottom. If we have a CH3 group, you can draw the polymer with the CH3 group in the same position. This is often how IB questions will be introduced. They'll say, draw the polymer made from this monomer, and you have to just keep the positioning the same of the side groups on the monomer. So final practice, deduce the repeating unit of the polymer made from the following monomers: acrylonitrile, so when that double bond opens up, we'll have it extend out each side. We'll have a CN group, top right, hydrogen bottom right, hydrogen top left, hydrogen bottom left. And that will repeat N times. Tetrafluoroethene, very simple, just fluorines attached above and below each carbon. Now, I made a little mistake here. You could actually just copy one single carbon, and that can be the repeating unit. So let me redraw that. This alone can repeat and create the whole polymer. So we'll just draw the square brackets on the left and right of that unit. N times will make the whole polymer. Butene, we've got this kind of structure here. Repeating unit of that, it's going to have two CH3 groups. When that polymer opens up, I think we can put them on the same side here. Then the other side will have just hydrogens. Then this extends many units to the left and right, N times. Okay, and if you look at this repeating unit, you can see it's actually just two of the same thing next to each other. So we can take half of this as the repeating unit and still recreate the whole polymer. I will mention that some sources will say the repeating unit must be the same size as the monomer in terms of like how many carbons are in it, the length of that chain. But others say the actual minimal repeating unit is the true definition. So I think you can use either, but if it's ambiguous or unclear, maybe just write which method you're actually using. All right, and number 2, deduce the monomer of the following addition polymers. Okay, so this looks kind of similar to the butene that we just drew, but the repeating unit here is fairly simple. It's going to be just this. So the monomer of that would most likely look like this. Carbon with 2 hydrogens attached, double bonded to another carbon, which has a CH3 group and an H on it. When that double bond opens up, it will create this polymer. Then B, it's kind of complicated structure, but If we consider bond rotations and things like that, the repeating unit should be from here just to here. Okay, so it looks like the monomer for this would be a CC double bond. It had to come from a double bond here for addition polymers. On the top, we would have C double bond O and OCH3 attached. Then we would have a CH3 group underneath, and then we just have 2 hydrogens attached to that left carbon. Okay, so if that CC double bond opens up, we should get this polymer here shown in B. And finally, 3, compare and contrast the bonding structure, IMF, and conductivity of ethene versus polyethene. So just very quickly to end this video, bonding structure of ethene is trigonoplanar molecule. Conductivity, low conductivity. Weak IMF. For polyethene then, we're going to have tetrahedral, long chain structure. And as I mentioned, it's hundreds of thousands of units long. IMF, strong. IMF, mainly London for that. It's still nonpolar. And low conductivity, similar to ethene. No mobile charge carriers. Okay, so similar things in conductivity, but quite different structure in IMF. All right, we'll finish there for today. So thanks for listening. Hope you learned something. See you next time.